All right, let's get right into it. Welcome to This Explainer. Today, we're diving into a genuinely fascinating journey, how we actually taught artificial intelligence to remember. We're going to trace the evolutionary tale of AI memory, going all the way from simple static reflexes to incredibly complex, gated long-term memory. It's a story all about hitting massive structural walls in computer science and then inventing brilliant architectural marvels to break right through them. So here's the ultimate question we're exploring today. How exactly do we get a machine learning model to not just process the present moment, but to remember the past so it can actually predict the future? You see, for decades, networks were completely stuck in the now. They had absolutely no concept of sequence. To understand how we finally solve that, we've got to look at how the technology evolved. This roadmap beautifully lays out our problem-solution evolutionary tale spanning almost 30 years. Every single leap in network architecture you see on this timeline, it was born out of a desperate need to fix a crippling limitation of the model that came right before it. From the 1950s all the way to 1997, engineers were basically playing a super high-stakes game of whack-a-mole with mathematical roadblocks. Section 1, the linear limits of perceptrons. To truly appreciate where we ended up, we have to start our story at the very beginning, looking at the biological metaphor of the simplest artificial neuron out there, the perceptron. Here's the blueprint of the perceptron. It is an incredibly elegant, simple threshold switching unit. It takes a bunch of real-valued inputs, multiplies them by some weights, adds a bias, and sums the whole thing up. If that sum crosses a specific predefined threshold, boom, it fires a 1. If not, it outputs a -1. That's literally it. It essentially just mimics a static biological reflex. But here's the perceptron's fatal flaw. It's entirely limited to linearly separable functions. Imagine a simple logical OR problem. You can easily draw one straight line to separate the pluses from the minuses, right? The perceptron handles that perfectly. But then take the XOR problem. You physically cannot draw a single straight line to separate those categories. Because of that one little detail, the perceptron gets completely stumped by nonlinear logic. To get around that linear limitation, computer scientists came up with multi-layer feed-forward networks. By adding hidden layers of neurons and swapping out that harsh binary threshold for continuous, smooth squashing functions, suddenly the network could learn highly complex, nonlinear stuff. Using a technique called error backpropagation, it could adjust its weights and learn from its mistakes. But there was still a huge problem. These networks were entirely loop-free. They were static, completely trapped in the present. Section 2. Adding time with RNNs. To actually model time prediction tasks, we desperately needed a dynamic classifier, and that leads us straight to the invention of recurrent neural networks. By introducing circular connections, RNNs finally shattered that static barrier. Instead of information only overflowing forward, signals from previous time steps were fed back into the network. Whether they were saving hidden layer outputs in context cells or just using direct self-feedback loops, this new architecture finally gave artificial intelligence a short-term memory. You can see how these literal loops create time right within the network's architecture. Because of these recurrent connections, the network actually holds on to an internal state at each classification step. It is constantly mixing what it's seeing right now with what it remembers from just a moment ago. But man, training these temporal loops was no joke. It required some serious mathematical power-ups. You basically had two choices. First, backpropagation through time, or BPTT. This is a really clever trick where you essentially unroll the RNN backward in time, creating a massive virtual feed-forward network so you can calculate weight changes offline. Or you could use real-time recurrent learning, RTRL, which skips the unrolling and instead does continuous heavy-duty math online as the data stream is actually coming in. Section 3, the vanishing error problem. Just as AI was starting to taste the concept of sequence in time, it ran face-first into a massive, villainous roadblock. It turns out standard RNNs were effectively capped at remembering only about 5 to 10 discrete time steps. This is where the math gets genuinely treacherous. When you propagate errors backward over many time steps to update the network's weights, those error signals scale exponentially. It cascades into a complete mathematical disaster known as the vanishing error problem. Think of it like a game of telephone played with 1,000 people. Because that error gradient is multiplied repeatedly across every single time step by the network's weights, one of two things is going to happen.
If the weights are slightly above 1, the error blows up. It explodes, giving you wild, unstable networks. But if the weights are slightly below 1, the error shrinks and shrinks exponentially until it vanishes to 0. And when the error vanishes, the network's global learning literally freezes. It just can't learn to bridge a gap longer than 10 steps.
Section 4, How LSTMs Save the Day. Right when it seemed like deep temporal learning was just impossible, the hero of our story shows up. Long short-term memory, or LSTM. This was an absolute architectural marvel designed explicitly to bridge minimal time lags of more than 1,000 discrete time steps. The pure genius of the LSTM lies right here in its core, the constant error carousel. Instead of letting weights multiply and vanish, the researchers asked a super simple question. What if we just force the internal self-connection weight to be exactly 1.0? By using a linear identity function and a fixed weight of 1, the CEC perfectly preserves the error signal backwards through time, indefinitely. It instantly solved the vanishing gradient problem because multiplying by 1 never shrinks and it never explodes. But fixing that weight to 1.0 created a brand new problem. The cell could now easily get flooded with conflicting updates and totally irrelevant noise. To stop this, the CEC was wrapped in multiplicative gates. I love to think of them as VIP club bouncers. They're units that scale signals strictly between 0 and 1, effectively granting or denying access to the carousel. You've got the input gate, protecting the memory from noisy data, the forget gate, which learns when to adaptively wipe the memory clean, and the output gate, which stops the cell's contents from leaking out and disturbing the rest of the network until the exact right moment. Let's look under the hood at the master blueprint. Right in the center, you can see the constant error carousel spinning away with that fixed weight of 1.0. And completely surrounding it are those intricate bouncers, the input, forget, and output gates. Training this beast actually requires a really complex hybrid approach. The network components after the cells use BPTT, while the components before and including the cells use RTRL. So what's the big thing you should take away from this explainer? It's the sheer compounding brilliance of this evolution. By solving the structural limits of perceptrons, and then engineering a mechanical fix to the vanishing gradients of RNNs, LSTMs finally gave machines a reliable, highly controllable long-term memory. It allowed AI to grasp the context of entire paragraphs of text, rather than just remembering the last few words. I'm going to leave you with a final thought here. Now that you understand the mechanical triumph of overcoming the vanishing gradient with LSTMs and how we literally forced algorithms to remember using constant error carousels and bouncer gates, just imagine how these foundational building blocks evolved into the incredibly deep, attention-driven AIs that are changing our world today. If we could engineer a mathematical loop to remember 1,000 steps back in the 90s, what are the limits of the models we are building right now? Thanks so much for exploring the architecture of AI memory with me today.